Till now we have seen how to draw the shear force and bending moment diagrams for beams and how to get stresses and deflection in them. Now we will see another class of problems which is caused by torques applied to bars about their longitudinal cross section. This class of problem is known as torsion, or the loading is known as torsion. Now what happens in torsion is we have a bar of particular diameter, for example, and we apply a torque to it, T. This torque is applied about the longitudinal axis, and torque T causes what is known as a twist of the bar. So if I draw a three-dimensional picture of this bar, I have this bar here, so it twists like that. So the point P, let's say, which was originally here, after some time comes here P dash, and this is the center. So if the radius of the bar is R, then there is a particular twist, and this angle, I just zoom that region, the angle POP dash, this angle is known as angle of twist or simply twist. It is denoted by theta. So take into the formula for bending, we have one formula for torsion also, which is given by T upon J is equal to G theta by L is equal to tau upon R, where T is the applied torque, J is the polar moment of inertia of the cross section, G is the modulus of rigidity of the material, L is the length, which is, let's say, this much. This is L. Tau is the shear stress at a particular radius. So for example, we can have a cross section like this, but we can find out the shear stress here at this location, which is at some radius R, which may not be equal to the radius of the bar. It may be somewhere inside the cross section also, and R is the location of that, the radius of that location from the center. So we can use this formula to figure out the shear stress in the bar because of the torsion. Now in this chapter we will exclusively focus on circular cross sections. So for a circular cross section of radius capital R, the value of J or polar moment of inertia is given by pi by 2 R to power 4. This is the cross section and the radius is R. Now let's say for this problem, if we have to figure out the value of shear stress at the top fiber, we say T upon pi by 2 R to power 4 is equal to tau upon R, and I get tau is equal to 2T by pi R cube, and that is the maximum shear stress which occurs in this bar. Now there are various modifications which are possible. For example, instead of a bar which is a solid bar, we can have a tube like this, a very thin tube, a tube whose thickness is some small number called T, and its radius can be R. So here I can modify the formula of J, which is given by pi, the outer radius to power 4 minus inner radius to power 4 by 2, by saying it can be written as like this. which can further be written like this. Now Ro minus Ri is the thickness. So this is equal to thickness, this portion, and I can always say that Ro plus Ri, rather Ro is close to Ri, is close to some average radius. This is Ro. Now, so that will ensure that I get J is equal to pi by 2. This becomes 2 times R average square multiplied by 2 times R average. This is 2 times R average, and this portion is 2 times R average square multiplied by T. So I get J is equal to 2 pi R average cube T. Now using this formula, I can find out the maximum shear stress in the tube. The formula is same, we just feed in the value in this formula for torsion. That is all. Now this is a simple problem right now because we don't have any complexity in loading here. But let's see if what happens if we have more complex loading conditions. Suppose I am given a bar which is sort of a step bar. So I have this kind of a bar. Let's say this length is L1 and this length is L2, and this radius is R2 while this radius is R1. Then I have a torque applied here T. So how do I get the, let's say, the angle of twist for this bar? So in this case what happens is we can draw the free body diagrams of the two bars separately. So I isolated two portions of the bars, the two steps, let's say. This bar has torque T, and please see that this is not a bending torque, it is a torsional torque, which means it is about the longitudinal cross section. So this torque is reacted here, and the same torque is transferred to the second step, and that is again reacted here. So in case of series connection, this is a series connection because here torque remains equal. So what is happening is that both the steps are carrying the same torque. Now from this we can, for example, for this case, for the bar which is fixed, for the step which is fixed, we know that we can find out the angle of twist using T upon J multiplied by L by G. So for this case it will be theta 1, which is the twist in the first bar, is equal to T upon pi by 2 R1 to power 4 into L1 by G. Let's assume that both the materials are same, so the value of G remains constant. So this is the twist for the first bar. It can be further simplified to say it is 2T L1 by pi R1 to power 4 G. Now the twist in second bar is equal to again the torque carried by it, which is T upon pi by 2 R2 to power 4 multiplied by L2 by G. But you have to keep in mind that this twist is with respect to the cross section here. So it is like first this bar is twisting, then over that this bar is twisting by theta 2. So the total twist here with respect to the wall here, so the total twist is equal to theta 1 plus theta 2, which is 2t by pi g rather, L1 by R1 to power 4 plus L2 by R2 to power 4. And this formula can be extended to any number of bars. Let's say we have 4 bars like this. We can extend it to theta 1 plus theta 2 plus theta 3 plus theta 4. So it will be theta 1, theta 2, theta 3, theta 4. We can extend the same formula in the similar way. And this example is similar to what we have seen for, like, what we know for the currents or for fluid mechanics thing, wherein the formulae are all similar in the form, which means that they have these kind of additive terms. So it's a very simple thing. So this is called series connection of the bars. Now let's see what happens in a different kind of connection, which is known as parallel connection. So I have this kind of connection now. I have one bar. I have the same arrangement actually, which is this is L1 and R1, R2, L2. Now I have both the ends fixed now, and I apply a torque here like this, T. So what happens in this case now is that both the steps take some portion of the torque, which means if I isolate both of them, this portion has taken some torque T1 and this portion has taken some other portion, some other torque, which is, let's say, T2. So what it tells is T1 plus T2 is equal to the total torque. That is because the torque is distributed between the two things in certain ratio. But the other thing to notice is that because they are rigidly fixed, which means that if I draw this section separately, I have this section where the connection is happening. So if I zoom this region, I will see that this is the larger section and this is the smaller section. So this is coming out here and that's going out there that way. So the twist in both of them, this is the twist, is equal, which means theta 1 is equal to theta 2. Now if I do this, use this condition, I know that theta 1 is equal to T1 upon J1 into L1 by, let's assume the modulus of rigidity is equal. So this is the first twist, and the second twist is T2 upon J2 multiplied by L2 by G. Because as theta 1 is equal to theta 2, I will say T1 by J1 into L1 by G is equal to T2 by J2 into L2 by G, which is nothing but T1 by J1 into L1 is equal to T2 by J2 into L2. Combine this with the other condition, which is T1 plus T2 equal to T. We can find out what is the ratio of the torques, like what is the value of T1 and T2 separately, which means that we can find out what portion of the torque is taken by each part. Now let us solve one example here, one question. So if L1 is equal to L2 is given, and I am given that R1, which means the first radius, is some n times R2, where n is any real number. It can be anything. It can be an integer, it can be a small, but it is more than let's say more than 1, which means that the step is like a decreasing step, which means that left portion is of higher diameter compared to the compared to the right portion. If I'm given this condition, I apply this condition here, so I know that T1, now L1 is equal to L2, so I know T1 by J1 L, let's say that both the lengths are equal to L, is equal to T2 by J2 into L. So this gets cancelled out. Now it is given that R1 is n times R2, so I can feed in that value here. I can say T pi by 2 n times R2 to power 4 is equal to T2 by pi by 2 R2 to power 4. Now this pi by 2 gets cancelled, so I know, and this I know that this leads to T1 is equal to n to power 4 T2, and we know that T1 plus T2 is equal to T. This also we know because this is a parallel connection. It is called parallel connection. I can do the series connection there. So using these two equations, I can solve these two equations for T1 and T2 separately. So this is a nice example, and it is the sort of problem which can be expected in GATE or other competitive examinations. Now let us see one more thing, which is known as power transmission using torsion, or rather the power transmission using the torque. Now if I'm given something like this, I will write once more. For example, given something like this. Now let's say that this is part of a machine, which means that this is connected to a motor, for example, and this torque is this bar is rotating with the speed of omega, where omega is let's say is speed of rotation in radians per second. Speed of rotation is given in radians per second. So the power transmission is equal to T omega. So the P is T omega. Now, obviously, if we are given P, then we can find out what is the torque in that. So if I use the same formula, T by J is equal to tau upon R, for example, to figure out what is the particular amount of stress in the bar which is transmitting power at P, which is transmitting power P at omega rotational speed. So I know that this T will become P by omega upon J is equal to tau upon R. I can modify this equation to find out what is the value of tau, which is P upon PR upon J omega. This is the amount of shear stress which is there in bar, which is transmitting power P at rotational speed omega. Obviously, this can be varied in some another sense, which is I can be given the number of rotations per second, which is called n. So in that case, omega is given by 2 pi n. That's the value of omega. So I can write tau, that is equal to PR by 2 pi n J. Now if we have to find out the maximum shear stress, then obviously J is pi r to power 4. So tau max is equal to PR upon 2 pi n into pi by 2 r to power 4. So that gives me tau max as P upon this 2 gets cancelled out, n pi square r to power r cube. So that's the formula for maximum shear stress, which is transmitting maximum shear stress in a bar, which is transmitting power P at the speed of, or the rotational speed of n, and which has a radius of r. Now this is a very nice formula to remember. It's easy that it's easy in one sense that the power of n is 1, the power of pi is 2, and the power of r is 3. So it's like p upon n pi square r cube. But what we need to remember is that we should not model up between n and pi and r. You should not make it like pi n square r cube or r pi square n cube, like that. This formula has to be, I mean, it is better to practice and then remember the formula rather than just remembering the formula to apply in some situation. That's not correct. One way to remember is that because the rotational speed is occurring as a linear quantity, its power, which means n's power, should be 1. So that is one way of remembering it. And r obviously has to be cubed because it is coming from j upon r. So this is about the torsion. Torsion is a very important phenomenon because torsion helps transmit powers. Most of the power transmission machinery and even the power generation machinery like turbines, which have long shafts of the coil or magnet rotating inside a coil or magnet to produce electricity. All these are loaded by torsion, and torsion is a very important loading condition. And this formula is very important formula. This tau max formula for power transmission. That's a very important formula to remember. Now, obviously, in this case, we can modify it further to have torsion, or rather the maximum torque for a tube instead of our solid shaft, which is like this. We can modify it suitably to get the power transmission for tube, wherein the j value will become pi into 2 pi into r cube t and all that. So in that case, it will become 4 pi square into n into r square. That kind of thing will come. So if I just write it quickly, tau max for hollow or tube is equal to, I modify this formula here, it becomes PR upon 2 pi n into j will be 2 pi r cube t, where t is the thickness of the tube, and if I modify it, it becomes 4 pi square n into r square t. That's the formula. So that is a formula for power transmission using a tube. Now let's solve a few simple cases of torsional loading and see if we can figure out the correct answer for them. So the first problem is like this. I have a simple bar which is let's say the length of the bar is L, and radius is some R1, some number. So I have a simple bar of length L, and it is loaded by some torque T, and the radius, let's say the diameter or the radius actually is R, some R. Now it is made of material which has Young's shear modulus of G1. Now the twist in this is equal to theta 1, which is T upon J into L by G1. Now the question is, if I replace this um, with a material which has G2, now G1 is replaced by G2, where G2 is 3 times of G1, and I will tell you why it is 3 times, because this is a case when G1 is aluminum and G2 is steel. Normally the value is 3 times. So now if I figure out for the same bar and the same length and the same uh, radius, if the value of twist changes to theta 2, which is nothing but T upon J, the J remains same because we are not changing the radius, multiplied by L by G2, so that is T upon TL upon J into 3G1, or the twist reduces by 1/3. Now here there are two ways of doing one thing, which is if I say that we have to make sure that the twists are equal, so I say that theta 1 has to be equal to theta 2. Now this is the condition I want. So in this case, now how do I do that? Obviously I make both of them equal to theta, and I say that theta is equal to T upon, now there are two ways. I can either increase or decrease the length, which means I can change the length or I can change the radius. So I want to show you how to do or in what case the material mass saving is more, which means that in what case means case 1 is we reduce the length or we reduce the radius. So let's say we reduce the length or change the length. So in first case I have this condition, which is T upon J remains constant now, multiplied by L1. First case is L1, wherein the first radius is first length is L1 for aluminum, for example, by G1 is equal to T upon J multiplied by L2 by G2. So in this case I get the L2 is equal to G2 by G1 multiplied by L1, or G2 by G1 we know is 3. So L2 is 3 times L1, which means that if I replace my material from a lower modulus material to a higher modulus material, to get the same amount of torsion, I have to increase the length by the same ratio. Now let's see if we keep the length constant but change the radius. So in that case, theta is equal to T upon, now it will become J1 multiplied by L upon G1 is equal to T upon J2 multiplied by L upon G2. So in this case, I know that both the numerator is constant, so J1 G1 is equal to G2 J2, or J1 is G2 by G1 into J2, which is nothing but which is nothing but 3 times of J2. This is J1 is equal to, I just need to check it carefully whether it's coming correct or not. This is J1 is equal to G2 J2, so J1 is equal to G2 by G1 into J2. This is G2. Now what does it tell? It tells that if we have to have the same twist but we change the radius now, so in this case now, the J1, which means that the polar moment of inertia is more. In previous case, the length of the second case was higher, which means we had to have a longer length bar of the higher or the stronger material. But if we keep the length constant, then the lower material or the weaker material's polar moment of inertia must be higher. Now this can be written as pi by 2 r1 to power 4 is equal to pi by 2 into r2 to power 4 into 3. So the ratio of radius r1 by r2 varies as fourth root of the ratio of the strength, while the ratio of length varies directly. So you see L2 by L1 is 3 times, while R2 by, or rather R1 by R2 is cube or fourth root of 3. So obviously the amount of material change with radius change is far lower compared to the length change. So the preferred method if you are changing the material is to change the cross section or change the radius, because that has fourth power or third power coming into picture. So this is an important problem, and we will see various applications of this when we solve gate questions.